Hi guys, this is Craig Robertson with UNMIEEE again, and welcome back. Today we're going to go over the basic principles of the SR NOR latch. That stands for reset, or set, reset, NOR latch. Now, the basic reason that we use latches is because they can remember. They can remember what the last thing was that we put through it, and that helps because having memory is very important. Well, I mean, obviously, your computer has to remember what you just told it, because it's not just this big combinatorial machine. It's clocked. It needs to remember what you told it, because what good is a computer if it can't remember anything, right? So let's go ahead and start going over the basics of this SR NOR latch, and it's pretty simple. So here are the inputs. You have a set and a reset. And then here you have Q next, designated by the plus sign there, and then you have Q present. So Q in the present state is what the latch is remembering. Now Q in the plus state is what happens, or is what the latch is remembering after we do our combinatorial logic over here. So let's go ahead and just say, for example, for the first example, and I'll use red for this. For our first example, say that we have a 1 that our latch is remembering. And let's go ahead and say that set is 0 and reset is 0. So we're not trying to set the latch, we're not trying to reset the latch, we're just leaving it in its common state, and we're just going to see if it remembers 1. Let's see if it does. So a 1, which is on this line here. Remember, these two aren't connected. They're not connected unless I have a little dot there, right? So the 1 is on this line, which comes right here. Now, with a NOR gate, a 1 and a 0 together, that creates a 0, just from the truth table of the NOR gate. So let's go ahead and come down here and watch where the line goes, and we have a 0 right there, right? So if our reset is a 0 and this signal from the other NOR gate is a 0, that will give us a 1, right? Just from the truth table of the NOR gate. Feel free to review those truth tables at any time. A lot of the times I have to just redraw them, and I just do it kind of quick as I, X and Y. And then I go NOR. So I go 0, 0, 1, 1, 0, 1, 0, 1. And that'll cover all the possibilities. And then I go ahead and say, alright, this is what a NOR gate looks like, right? So that's a 1, and then a 0, 0, 0. That's the truth table for a NOR gate. So if we look right here, we can double check and say, alright, 0, 1, 0, 1, that returns a 0. Then we can go ahead and say 0, 0. Okay, 0, 0, well, that returns a 1. So now we know that our function is correct. Now this little box here that says delta t on it, this little box right here, this just means that there's kind of a time delay between putting it into the circuit here and by the time we get it out. And you'll find that's true in later classes. But for right now, let's just assume that from the time that Q is input into the gates, and by the time it comes out this lower gate here, there's just a little bit of a time delay. So if we look at Q versus our Q next, after the time delay, we can see here that they're both 1. That means that with no inputs, our latch here remembered that it was supposed to be a 1. So let's go ahead and let's try something else. Let's go ahead and try putting a 1 on the reset and a 0 on the set, and then let's go ahead and leave the 1 right here at the beginning. So I'll leave it there in red so that we can tell versus our operations. So for our first operation, it was going to be set equals 0, reset equals 0, and Q equals 0. And all that together made a Q plus equal to 1. I'm sorry, Q was equal to 1, wasn't it? So let's make sure that we have that right. So Q was equal to 1 for that one. That's my fault. Alright, so for this one, let's go ahead and say that set equals 0, reset equals 1, and Q is still equal to 1. And let's go ahead and map it out and figure out what happens. So, our Q is 1. That'll go ahead and follow it up there. And so we know that our Q here is 1. Now a 0 and a 1, that's exactly the same thing that we had before, so that puts a 0 on the output, right? So let's go ahead and follow the 0 down here. Let's put the 0 right there. So this right here will give us a 0 and a 0. Well, that's a 1. Oh, I'm sorry. I was looking at the wrong one. That right there will give us a 0 and a 1, right? Because we're looking at the black ones right now. So a 0 and a 1 will go ahead and give us a 0 out, right? Because a 0 and a 1 for a NOR gate will give us a 0 out. Now, after some time delay, that 0 will go to Q. So then that'll bring us a 0 right here. So you see that by putting a 1 on the reset and putting a 0 on the set, and then we changed our Q of 1 into a Q of 0, right? So now we know that that makes a next state, a Q plus, equal to 0. Now, this is it's kind of confusing, so go through each one of these possibilities yourself at home as well. That way, you can kind of prove it to yourself. You know, maybe if you're on a test and you totally space it, then you can kind of reprove it to yourself. So let's go ahead and stay with the idea that we have a 0 right here. I'm going to do this next one in blue. So let's say that we have a 0 right there, and we're going to go ahead and say this time that set will be equal to 1, that reset will be equal to 0, and that Q will be equal, and right now Q is 0, so we're going to go ahead and call it 0. And let's see what this function puts out for us. So let's go ahead and write all of our inputs up here. Set equal to 1, reset equal to 0, and then Q equal to 0 like we have right there. Alright, so let's follow this signal up. We have a 0 right here. So a 1 and a 0, give us a 0 right through a NOR gate. So we have a 0 right there. Now we take that 0 down, we go ahead and put that 0 right there. So our reset's a 0, and this signal of this other NOR gate is a 0. So this gives us a 0 and a 0, which returns a 1, right? Now, we can go ahead and bring that 1 up here, and you see how our previous Q was a 0, but our Q plus is a 1? Well, what we just did there was we changed our Q from a 0 to a 1. And this is important because it shows us that our Q plus is equal to 1. So, what we can kind of tell right here is that if set and reset are 0, then and Q equals 1, then Q plus will remember 1. Now, I'm not going to prove it to you. You can prove it to yourself just out of the textbook. It does a really good example. But the textbook will prove to you that if Q is equal to 0, Q plus will be equal to 0. So, if we're not putting a 1 on either set or reset, it remembers, and it'll keep on remembering until we change one of these. Now, if we put reset equal to 1 and set equal to 0, then what we find is that we change Q from a 1, and then the next state of Q will be a 0. So we're resetting it, we're turning it off almost. We're just kind of hitting the off switch when we put a 1 on that reset. Conversely, for set equal to 1, reset equal to 0, and Q equals 0, we get the next state of Q being equal to 1. That's like pressing the set switch, or turning it on. So, what we can tell here is that we have kind of something that's acting kind of like a toggle switch. It's remembering what we want, and we can turn it on, we can turn it off, we can do quite a few things with it, allowing us for quite a bit of flexibility when it comes to actually working with this thing. So you can see how useful these latches are, and how we can use them in computers, you know, just by looking at the truth tables here. Now our final one, and I'll do this one in purple, is we're going to look at the forbidden state of this flip-flop, of this latch here. Now these latches, whether it be an SR NOR or an SR NAND, they have a forbidden state always, and the forbidden one for the SR NOR is when set and reset are both equal to 1. So this is kind of like turning the off and on switch on at the same time, and you're not quite sure what'll happen, but so I know what'll happen, and I'll prove it to you. So it S equal to 1, and let's go ahead and do R equal to 1, and since Q is already 1 in our example here, we'll just say we'll go ahead and say Q equals 0 just to kind of show you what actually happens. So, let's go ahead and say the Q is equal to 0 right now. So this is the one we're going to follow, the purple one. And S is equal to 1 and R is equal to 1. So let's go ahead and put these up here. S is equal to 1. R is equal to 1. So let's go ahead and map it out. So a 0 goes up here onto this signal right here. And let's see, a 1 and a 0. 1 and a 0 return to 0, right? So no change there. And then we go ahead and we go out. We bring it down here. So that's our new 0. So a 0 and a 0 creates a 1, right? 0 and a 0 gives us a 1, which gives us a 1 right here. Which means that our 0 there and our 1 at Q plus means that we bring that over here and we get a 1. So that means that Q plus equals 1. And that's the thing to remember about the SR NOR latch, is that if you put it into the forbidden state, if you turn the set and reset to 1 at the same time, it is a set, it will set before it resets, and it always sets when you're in the forbidden state. So it's set dominant is actually what the book calls it. But always remember that if you stick an SR NOR latch into this forbidden state, you're never supposed to, and in fact in future chapters we create circuitry to prevent that. But for the time being, it is set dominant, and it will always go to 1. If you have any more questions, make sure to visit us in room 312 in the ECE building at UNM, the main campus. And happy studying, guys. Good luck, and send me your questions if you have any. Thank you very much.